example 5 here. Let's continue moving on. We're not dealing with those rational functions, the top heavy, bottom heavy balanced anymore. We're dealing with some of the trigonometric functions. So let's think about the limit as x approaches infinity of sine of x. Well, I know what the sine of x looks like as a graph, right? It just oscillates, keeps on going between the y values of 1 and negative 1. And so as we go to infinity, the question is, does it approach a single value? Well, the answer is no, this does not approach a single value. And because it doesn't approach a single value, there is no horizontal asymptote, or we could say that the limit as x approaches infinity does not exist. So the answer for A would be does not exist. But now let's think about the limit as x approaches infinity of sine x over x. Remember here, as we're looking in the numerator, sine of x is something bounded by negative 1 and 1. So that's a number that's always bounded by negative 1 and 1. And x, this number is going to be getting larger and larger and larger. So as this number gets larger and larger and larger, we really have some constant over something that's approaching infinity. So what should happen is this should go to the number 0, but we want to make sure of that. And how can we make sure of that? Again, what we could do here is we could look at x values if we want. We could look at 1, 10, 100 and keep on going on and seeing what this looks like. You could plug this into your chart to see what happens, and hopefully what we see is this goes towards the number 0 here. But what I want to do is I want to bring back something that we saw in a previous section. This is a beautiful example of something we saw in the previous section. And what I want to bring back is something called the squeeze theorem. And if you remember the squeeze theorem, what the squeeze theorem was is if you can find something bigger than it and something smaller than it that goes to the same thing, then the middle thing must go to it. So graphically, what the heck am I talking about? Here's what I'm talking about, is if we can find this top function, let's call that f of x, and we can find this bottom function, let's call that g of x, and if we know our function is something in between them, and this would be sine of x over x, if that's something between them, and if we know the top function and the bottom function, f of x and g of x, go to the same thing, then we know that sine of x over x must go to that same thing as well. Well, here's something that I'd like you to investigate. I'd like you to consider sine of x all over x. Again, that top, the largest value that top can be is 1. So this would always be smaller than 1 over x. So here, I'm going to say my bigger function is 1 over x. Likewise, remember, sine of x over x, think about sine of x over x, that always has to be bigger than or equal to, well, the smallest that it could be is if the top was a negative 1, right? So sine of x over x is always bigger than or equal to negative 1 over x, so I'll call that g of x, right? Let's call that one g of x. So the idea is, let's consider the limit as x goes to infinity of 1 over x, and let's consider the limit, which is our upper function, that f of x function, right? And the limit as x goes to negative infinity of negative 1, or sorry, the limit as x goes to infinity of negative 1 over x. That's our bottom function. That's the g of x in the picture, right? Well, each one of those would go to 1 over infinity, which would be 0. This one would go to negative 1 over infinity, which still goes to the number 0. So what have we shown? We've shown this top function goes towards a y value of 0. We've shown that this bottom function goes to a y value of 0. So what does that mean? That means the function in between, by the squeeze theorem, also must go to the number 0. So because the limit, let me show the formal statement here, because the limit is x goes to infinity of negative 1 over x is always got to be less than or equal to the limit as x goes to infinity of sine of x over x, which is less than or equal to the limit as x goes to infinity of the bigger one, which was 1 over x. And we know this goes to 0 and this goes to 0. What we have is 0 is less than or equal to the limit as x goes to infinity of sine of x over x is less than or equal to 0. So that, by the squeeze theorem, I'm just going to put THM for theorem, implies the limit as x goes to infinity, sine x over x equals 0. So that's a really cool example of the squeeze theorem, a beautiful introductory example of when and how would we use the squeeze theorem. That is exactly it right there. We found the function f of x above it that went to 0, the function g of x below it that went to 0. So that means that the middle function, which is sine x over x, also must go to 0. Did I expect you to think of that? Do I expect you to do that on the test? If you did, cool, might even try to give you a little extra credit if you could pull that one out. But no, you could have used the chart value on this one, the table value, and just done the table to get the answer on that problem. Okay, let's look at example 6 then. It says oxygen level in a pond. It says let f of t measure the level of oxygen in a pond where f of t equals 1 is normal unpolluted level, and the time t is measured in weeks. When t equals 0, organic waste is dumped into the pond, and as the waste material oxidizes, the level of oxygen in the pond is f of t equals t squared minus t plus 1 all over t squared plus 1. What percent of the normal level of oxygen exists in the pond after 1 week, 2 weeks, 3 weeks, and what is the limit as t approaches infinity? So what do we do here? All we have to do is plug in the values that they're looking at. I'm just going to use a chart here. I'm going to have t, and then I'm going to have f of t, where f of t was t squared minus t plus 1 all over t squared plus 1. Okay. The only reason I'm doing a table is because I have to plug in several numbers to the exact same function. So what numbers am I plugging in? Well, I'm plugging in the numbers 1, 2, and 3. And then the last, so that was part A, essentially parts A, B, and C, right? So here's A, B, and C. That's what they wanted to know, 1, 2, and 3. But then what's the fourth thing they wanted? The fourth thing they wanted would be D here is what I'm going to call it. And that's they're looking at what's the limit as t approaches infinity of t squared minus t plus 1 all over t squared plus 1. Okay. So let's do this one step at a time. Let's evaluate it at 1, 2, and 3 weeks. The way that I'm going to do this is I'm going to hit the table feature on my calculator, clear out everything that's there. I'm going to do a fraction. On top, I'm going to do x squared. X is t, right? So I'm doing x squared minus x minus 1. And on bottom, I'm doing x squared plus 1. I hit enter. Start doesn't matter. Step doesn't matter. Make sure you have ask x on there and then hit OK. Okay, I'm going to go in here. And I'm going to type in 1, enter, 2, enter, 3, enter. I do have fractions, so I want to go to those fractions. And I want to type in, I got to hit the double arrow button to see what it is. So I move up towards the first fraction, which I got was 1/2, hit the double arrow button, and I know that it's 0.5. So what does that mean? That's about a 50% of the oxygen level. We go down to the next one, and I had a fraction of 3/5. Hitting the double arrow button, I'm getting 0.6. That's about 60%. Okay. And then the next question asked after 3 weeks, which is actually different than what's in the book. In the book, it says 10 weeks, but I typed up 3 weeks, so let's do 3 weeks. When I do that and I hit the double arrow button, I'm getting 0.7, which means there's about 70% of the oxygen. Okay, so let's see what happens now. The idea is they dump the waste into the pond, so immediately it has a really, really bad effect on the oxygen level, right? But gradually that kind of degrades and we get more oxygen back into the pond. But the question then would be, okay, well, how much of it is actually going to come back? Is that waste, that pollutant, going to totally go away? Am I ever going to be back to that 100% oxygen level? So that's what we're investigating when we look at the limit as t approaches infinity. Well, what's the limit as t approaches infinity? The first thing that I'm going to notice is I'm going to look at it would be infinity over infinity, right? But what I noticed is that this is balanced. I know that this is balanced because I have a t squared on top and a t squared on bottom. So what do? I take the leading term on top, I take the leading term on bottom, so that's t squared over t squared, which does equal 1, which means it would approach infinity. Or sorry, which means it would approach 100% oxygen levels. So as time increased, eventually it would get back to normal. This is one of the few instances where you could get rid of everything, but that's what it means. So after 1 week, 50% oxygen levels, 2 weeks, 60% oxygen levels, 3 weeks, 70%, so it's gradually coming back. Eventually, everything would come back and you'd be back to 100% oxygen levels.